Hello and welcome to a new video in a graduate series on probability theory. Today's video is going to be about the notion of independence, and then we're going to move to talk about expected values. We're going to define expected values of random variables in the measured theoretic sense, and then we're going to recover the famous computational form of expected values. So we're gonna start off by talking about independence. You might have seen this notion in an undergraduate on an undergraduate level, but my purpose here is to give the proper definition, the generalized definition of independence. Of like sets or of sigma algebras and of random variables. So let me, I guess, start by saying let us fix probability space P omega F. F is the sigma algebra, and P is just the probability measure on this space. And what we're gonna do is the following. So maybe let us recall over here how you might have seen it in an undergraduate level. So you might have seen that two sets A and B are independent if the probability of A intersected with B is equal to the probability of A times the probability of B. Well, that's fine. This is okay. But you might have also seen the notion of pairwise independent, because if we're talking about more than two sets, for example, if we're talking about three sets, what does it mean for this for these three sets to be independent? You might have seen the notion of pairwise independent, namely that we say these three sets are pairwise independent if any two of them if any two of them are independent, if any two of them are independent, and in the sense of the first definition. So these two definitions might be familiar to you from an undergraduate probability course. Now it turns out that the notion of pairwise independence and independence are not the same. Like something like some sets can be pairwise independent, but they need not necessarily be independent. So what does it mean for like a collection of sets to be independent? So let us define it as follows. We say like A1 through AN, these sets are independent. Like if you start with these sets in the sigma algebra, these sets are said to be independent if for any subcollection of these, if we consider any subset of the set of indices and we look at the probability of the intersection, then we must get that this is the same as the product of the probabilities. So you might wonder, how is this different than pairwise independent? Well, this is different because pairwise independent only require it only requires that the probability of the intersection of two of them is the product of the probabilities. But over here, we're requiring that the probability of the intersection of any combination of these to be the product of the corresponding probabilities. So this is the notion of independence for sets. But we can actually generalize it, and we can talk about the notion of independence for collection of sets. Like if I take subsets of the sigma algebra F, and like if I call them A1 through AN, then we say that these sets are independent. These sets are independent if the following happens. If for every, I guess, let's say it this way. So for every collection AI I and I in the product of these collections, if we take any, like I should probably write it as like as a bracket thing, but it doesn't matter here. So if we take any like sets, so if we, first of all, we choose a collection of these, any collection that you want, like choose any set of indices and then look at the corresponding collections. And then in each of these collections, choose any set, like these are collections of sets, right? Choose any set in each of these collections and call them little AI, or excuse me, call them AIs. Then we must have that these that this collection of sets are actually independent. Then we must have that the probability of the intersection of these is the product of the probabilities. All right. So we're just, it's not really a deep thing. It's just that we're generalizing this notion of independence from sets to collection of sets by requiring that if we take any, like if we choose any sets like from an already chosen like collection of sets, then like they must satisfy this property. All right, so this is what's so-called independence of collection of sets, and we can particularly talk about independence of sigma algebras. So these AIs can actually be sigma algebras, and it totally makes sense to talk of this. So why are we doing this? Well, the reason we're doing this is because we want to define what's so-called independent random variables. Because you might have heard of this notion, but we want to make it precise. We want to make a definition here. So a sequence, a list of random variables is said to be a list of independent random variables. Like if we have these random variables, we say these random variables are independent if the sigma algebras generated by these random variables are actually independent. But what does that mean? Well, recall that, so let me remind you, if we look at the, maybe let me write it this way, sigma of xi is basically the sigma algebra generated by the sets xi belonging to, let me just say it, B, such that B is Borel. B is in the Borel set. So in other words, it's just the sigma algebra generated by the pre-images of Borel sets. So what are we saying here? We're saying that what we want in this case is that we want the following. So maybe if I write it in more details, it's gonna become clearer. We say that x1 through xn are independent if the probability of let me write it this way. x1 in b1, x2 in b2, dot dot dot, xn in bn is equal to the product of the probabilities, the product of xi in bi, as I ranges from 1 to n, and this we want this to happen for any collection of Borel sets, for any list of Borel sets. So we want for any Borel sets b1 through bn that this is satisfied. And notice here, like we can basically take the bi's to br itself, and in which case we'd have that this set is just the full the full set omega, and hence we know that the probability of omega is 1. So what I'm saying here is that this generalizes. There's no need to look at sub indices or subsets of the indices. So let me say this one more time. So we're gonna say that the random variables x1 through xn are independent if the sigma algebras generated by these sets, these pre-images, are actually all independent, and this precisely translates to this if you recall how we defined collection of sets to be independent. All right. So this is what it means for random variables to be independent. And now we're gonna move to talk about expected values. So we're gonna see that this notion is actually important when like sometimes when computing expected value of like the product of random variables, we need to find a way of finding that, and it turns out that the notion of independence is useful there. So what is expected value to begin with? Now I understand that you might have seen this definition in a nicer form. You might have seen it as the integral of x times the density function, and that is fine because we're gonna arrive at that in a few. But before that, we need to give the very general definition of expected values, and this is basically the integral of the random variable. So given a random variable x, okay, so remember we're still under the we were still like working with this probability space. So given a random variable x, now recall in a previous session we defined that random variables are just measurable functions. So this is just literally a measurable function. And what can we do to measurable functions? Well, we can integrate them. The random variable is just a measurable function, and we can integrate the measurable functions with respect to the measure. And this is what we're gonna do. We're gonna take this measurable function and we're gonna integrate it with respect to the measure dp. Of course, we're gonna integrate over omega, and we're gonna call this the expected value of x. Okay, so this is the high-level definition. This is the very general definition of the expected value of a random variable. This is the measure theoretic definition. Now, I wanna show you how one can move from this definition to the definition that you might have seen before, which is of this form. I want to show you how one can really justify why this general definition is the same thing as this one under some conditions. So this is what we're gonna show. So This thing is not necessarily always true, in the very general case, but it's true in in most of the practical applications. You would have this, but in the very general theoretic sense, this is what the expected value is. It's just the integral of this measurable function that we are actually calling a random variable. All right. For us to arrive at this already familiar definition, we need to prove a change of variable theorem. So let me state the theorem and then I'm gonna prove it. So if we have a random variable x, and it's it's a random variable of some measurable space SS, and it has a distribution mu. Remember, what does that mean? It means that, so maybe I can justify it here. It means that the measure of any set, is just the probability. So the measure of A is just the probability of the pre-image of A under X. This is what the distribution of X is. This is from the first session in the series. All right, so again, we're starting with a random variable defined on this measurable space, and we're assuming that it has a distribution mu. We're just giving the distribution the name mu. And suppose that f is a measurable function that is real valued. It's a measurable function defined on S, and it is real valued. Maybe I should, just to avoid confusion, maybe let's call this G, just to stick to the notation. So suppose G is a random variable that is, excuse me, it's a measurable function that is evaluated on S and it's real valued. And let's suppose in addition that one of these conditions hold. It's either that G is non-negative, or the expected value of G is less than infinity. Notice here we don't have this definition. What we have at this moment is this one. This is the only definition that we have. Anyways, so so let's suppose also that the expected value of G is less than infinity. Then we have this nice formula that the expected value of G can be computed as the integral of G of little y, d mu of y, where mu is this measure. Okay? So one more time, what is happening here? We have this measurable function G, and what can we do to measurable functions? Well, we can integrate them, and this is what we're gonna do. This measurable function, we can integrate it with respect to the measure mu, and we're gonna claim that this integral is gonna be the expected value of G of X. And from this formula, it's gonna follow right away that for some type of random variables, we have exactly this formula that we already know. So maybe let's leave the theorem a bit and let's talk about a definition, I guess. And then I'm gonna talk briefly about the proof of it. So remember from measure theory, when we say we say mu is absolutely continuous to some Lebesgue-Stieltjes measure f sub x dx, if mu of a is the integral over a of, or maybe let me say it this way, if d mu is equal to fx dx. In other words, the Lebesgue-Radon-Nikodyan derivative of mu is f of x. So a random variable is said to be absolutely continuous if its density, if its distribution that is defined as such, if its distribution is absolutely continuous to some Lebesgue-Stieltjes measure, and this is what it means in the measure theoretic sense, and that is to say, in that case, what we can do is that instead of integrating with respect to d mu, if we assume the theorem, if we assume that this theorem is true, the change of variable formula is true, then we can get right away that if x is absolutely continuous, i.e. if mu, the distribution of it, is absolutely continuous, then the expected value is going to be the integral of g, but instead of integrating with respect to mu, we can integrate with respect to fx dx. Of course, we're integrating here over r, and we can also write this as minus infinity infinity if you prefer that. And we just recovered the law of unconscious statisticians, right? This is how we get the expected value of this function of random variables, particularly when g of x, maybe let's use y, when g of y is just y, it's just y, it's just the like the linear function y, then the expected value of y, which is the same as the expected value of g of y, by definition of g here, is gonna be, by this formula, the integral from minus infinity to infinity of g of y times f sub x of y dy, but I guess g of y was y in this case, and we recovered the famous formula for computing expected values of random variables that are absolutely continuous. Excuse me, I should have said here that this is expected value of x, the random variable x. So as you see, this formula, it's actually useful for computation of expected values and so on. It's just like the same thing as this one, but for absolutely continuous random variables. And this is nice. Okay, so let's get back to the theorem, I guess, and see why it is true. Well, I'm not gonna go over the whole details, but I just want to mention that it's not that bad. It's not that bad to see this. So maybe I'm gonna just do it for like indicator functions, and then leave the rest. I'm gonna tell you how the rest are usually done. It's basically the usual measure theoretic trick of getting it. So we want to verify this thing for indicator functions. So let us go ahead and do that. So what's the expected value of g of x in this case? And remember, the only definition here that we have is the integral of this thing. So this would be the integral of g of x. So g here is the indicator function, so it would be the integral of chi sub a at x dp, and then this is the same thing as the integral over the set that is the pre-image of a under x. And why is that? It's because by definition of the indicator function, this is one only if the image of x is in a, right? And it's zero otherwise. This is the definition of indicator function. If the image of x is in a, then it's 1, and it's 0 otherwise. And hence we're just integrating over the pre-image of A under X, and this is we're integrating the function 1 in this case, and in that case this would be just the measure of that set. So this is what we have. Cool. But on the same, on the other hand, what we know is that the probability of this set, by definition of the distribution function from here, the probability of this pre-image is just mu at A. And we already know that mu at A is, of course, the integral of chi A d mu. So it's of course the integral on the right hand side, and this is because this is by definition, right? Because the integral over this indicator function would be the integral over A d mu, and that would be the measure of A. All right, so this proves it for indicator functions, but then it follows easily for for simple functions. But why is that? Maybe this is an important thing that I should mention here. So you already know from an undergraduate level that the expected value is linear. It's basically like if you take the expected value of x plus y, it's the expected value of x plus the expected value of y. If you have like real non-negative random variables, then you have some monotonicity of the expected values and so on and so on. But why is that? Well, it's true because it's just an integral, right? So if I were to put instead of x here x plus y, I can of course separate the integrals and get the expected value of x plus the expected value of y. So every property that the integral has, of course the expected value will have it, right? So that's natural. In view of this, we can observe that if we have simple functions which are linear combinations of indicator functions, then this property continually to hold trivially by linearity, and then it follows for non-negative. It follows by convergence theorems for non-negative functions, because we're assuming this thing. This is very important. We're assuming this, for which we can use, for example, dominated convergence, or if we're assuming this, we can use something like monotone convergence theorem. So in either case, we have convergence theorems to get the result for for non-negative functions, and then so on and so on. For real functions, we can write it as the difference of the positive part of the function and the negative part of the function, and we get it for real functions. We get it for integrable functions in general. So this is the usual measure theoretic way. So I'm not gonna write down the details, but you're encouraged to do so. Okay, so now we just recovered the famous expected value formula for for absolutely continuous random variables.